So part 2, kicking off on the higher paper for the sample assessment materials with a 6 marker on question 5. So evidence supports Big Bang. So there's 2 pieces of evidence. You're gonna have your absorption spectra and your CMBR, your cosmic microwave background radiation. So I'm going to talk about absorption spectra first. I'm going to talk about what it is and how it relates. So it's quite lengthy. I've tried to stick everything in here. You can see that it's quite a bit. So continuous coloured light cross with black lines. That's what absorption spectra is. These lines represent different elements absorbed from an object. So when I say object, that could be a planet or that could be a galaxy from the object's atmosphere. If the wavelengths of black lines are shifted to the red end, so increased wavelength, so bigger wavelengths of the spectrum, it means that the object is moving away from us. And it says the bigger the redshift, the further and faster it is. So the further it's moving away from us and the faster it's moving away from us. How does this relate to the Big Bang Theory? Well, the waves have been stretched more, suggesting that the universe is expanding. So if something's moving away further from us, faster from us, the further it is, it's got to be expanding, and therefore we can say that the origin, if we reverse this, it must come from a single point. In terms of cosmic microwave background radiation, this initially, so this is like the leftover footprint or fingerprint from the Big Bang, and initially it would have been gamma, really high energy and short wavelengths. But as time has progressed, the wavelength has been stretched by the expanding universe. That's referring to that sort of redshift, and has now increased to a microwave region. So it would have gone through every one of those EM spectrums until we get to microwave, and one day it'll become radio wave. It'll be stretched that much. And this can be detected in uniform amounts everywhere. So I think, you know, if you write something like that, you're going to get close to the 6 marks. But again, because it's the quality of written writing there, or extended writing, it's you got to take your chances with the examiner, really. But my advice, get as much as you can down, and maybe put it in bullet points so it's nice and clear, or just be clear on what you're saying. Okay, we've got a rocket and we've got a weight. So the rocket weighs this. So the resultant upward force has got to be bigger than the weight, because if it's moving up. So let's have a look what it's saying. It's got 2 boosters at 12.5 meganewtons, and it's got 3 engines of 1.8 meganewtons. I know there's a couple more bits in here, but really it's asking for the total thrust. Now the total thrust is different from a resultant force because it is just it's what's the force taking it up, really, without taking weight into account. So we want the total upward force is going to be 2 times this booster and 3 times this engine at 1.8 gives me 30.4. So let's keep that, and that's why I've underlined it in pink, because when we go to this one now, using equation page 2, which is going to be F equals ma, because we want the acceleration, it's given us gravity here is 10 newtons. So in order to use F equals ma, first of all I need the mass of the rocket. Now it's giving me a weight here, and weight, we should know from our practice, is mg, so mass times gravity. Well, if gravity's 10, and we want to know the mass, but we know the force, because force is equal to weight, so that should be W actually, W equals mg. It's going to be, if we stick the force, which is the weight of it, 3 times 10 to the power 7. Where'd you get that from, sir? I got it from there, look, in orange. And then we stick it over 10, we should find our mass to be 3 times 10 to the power 6 kilograms. Now I know my mass. What about my resultant force? So my resultant force is the upward force minus the weight. So remember I worked that out on the first page, 30.4 per there. That's my total upward force. But I've got my total upward force. To get my resultant force, now I take my other force from it. So it's 1 minus the other. So I'm going to minus 3 times 10 to the power 7. That gives me a resultant force, an overall force of 4 times 10 to the power 5. Now I know my force, now I know my mass, I can calculate for acceleration. So just a quick rearrangement there, A equals F over M. So now I'm going to take these figures I just worked out. So 4 times 10 to the power 5. But there, I should have done that in green, shouldn't I? And then 3 times 10 to the power 6, which was the mass. Should have done that in yellow, shouldn't I? And that gives me an initial acceleration of 0.1333333, and so on, meters per second squared. Now, calculate the mean acceleration. Mean acceleration. So you're thinking, I just calculated my acceleration there, but that was my initial acceleration. Now I want to do my mean acceleration, and I want to use all this information because it's going at 7,500 meters per second. And it's got a time somewhere. Yeah, I know the time is 6 minutes. 6 minutes, so 6 times 60. That's where I'm getting that from. So my change in velocity over time, because that's my mean acceleration over the 6 minutes, comes out to be 20.8 meters per second. During the first 6 minutes, the rocket produces a constant thrust. Explain why the mean acceleration over the 6 minutes is bigger. So again, a really common question here. Mass is getting less because the weight of the fuel is getting used up. Therefore, the resultant force is going to be continually increasing. So that acceleration happens. And again, you could prove this by doing a simple. So if we keep the force the same, the resultant force the same, you can see that if the mass goes from 2 to 1, to get the same force, the acceleration has got to go up. So 2 times 5 is equal to 1 times 10. So acceleration, so they're inversely proportional. If you dip or decrease the mass, you've got to increase the acceleration to get to the same force. That's what that's saying there. Isotopes. What are they? They both have the same... Oh, I didn't want to do that, did I? They both have the same number of protons. So in this case, iodine's got 53. So it must be an isotope of the same element. Iodine 131 has 8 more neutrons than iodine 123. How do I know that? 123 minus 131 is going to give you 8. So just for 2 marks, knowing what's in the mass number, really, protons and neutrons, and then your small number is your proton number. In physics, we call this the nucleon number. What's beta radiation? Is a fast-moving electron. If you don't get that, then I don't know. Wasting my time here. We've got everything on this side's got to equal everything on this side. So something plus 0 is 131. Sorry, 131 equals something plus 0 is 131. That's what I should have said. 53 equals 54 plus minus 1 is the only way you can get to 53. Why are we going to use gamma instead of beta? We're going to use gamma because gamma is less ionizing, so will not cause so much damage to human cells, is your answer there. Other reasons could be it's easily detected because it's more penetrating as well. So it penetrates through the skin more. What does it mean? And again, this is just the definition of half-life. What's definition of half-life? It's going to take 8 days for the mass or the activity or parent nuclei of iodine 131 to decay by half. Then we've got the table for 2 marks, because this is not too bad. So it's saying that it's, well, we know it's got a half-life of 8 days. And it needs to get down to about 3%. So we will start at 100%, 50, 25, 12.5, 6.25, and then that's around about 3% there. So I've said 40 days, which was correct to the mark scheme. And this last one on fission then. Why do we need... so which part of the nuclear core is designed to reduce the neutron's high energies? This moderator is going to slow down those neutrons in order to be captured by the uranium nucleus. How do I know it's uranium? Because it's right by there, like uranium. Only 1 of 3 neutrons release is needed. So what we're going to do the others, you're going to use control rods. These are often boron. And by the way, graphite is a good moderator. I think sometimes it can be water. Control rods are used to absorb the excess neutrons. How are you going to shut it down completely? You're going to insert the control rods fully. You're going to fully drop them into the reactor. Nice questions there. Write a balanced equation. Now, I've color-coded these up just to show you where I'm getting them from. You might be thinking, oh my God, have you got to remember all this? No, you haven't. Because it's given to you here, look. It's telling you uranium's worth 23592. That's going to decay into krypton and barium, both with these mass numbers. And you've got, it's even showing you, it's got 1, 2, 3 neutrons there. Now, a neutron's got a mass number, but it's not got a proton number because it's not a proton, is it? So it's just got that mass of 1. And that's exactly what I've done. I know it's a little bit sketchy there because so that's 0 and 1 neutrons. So 3 plus 144 plus 89 should give you 235 plus 1. So all that should balance out. Oh, this question then for 2 marks is all about recognizing kinetic energy equals half mv squared. Masses you can get from the mass numbers. So I've picked 144 there and 1 for a neutron. So I said barium's got to equal neutron. Let's get the ratio. As soon as we do this, we'll get a ratio. Half mv squared has got to equals half mv squared this side. So 0.5, which is your half, times 144v squared equals 0.5 times 1, because that's my mass number of a neutron, v squared. Simplify that. So I've got 72v squared equals 0.5v squared. How do I get rid of the v squared to just get v on its own now? It's square root of 72 equals square root of 0.5. Now I've done that, I can cancel the v's out. So I literally now, how many times does so I've got 8.5, which is the square root of 72, equals 0.7. How many times does 0.7 go into 8.5? It's going to be 12 times. So there's your 12th. And that's proving that is a 12th of it. So thank you for watching. I hope you've got something out of this paper. And good luck.